So, good morning, you guys. I thought this would be better via video instead of class because I kind of felt like it would feel like video anyway in class because it's so difficult to communicate a little bit more so onto Zoom. So, I'm going to go over this also with you. And you should, as you go through this, you guys, Coulomb's law is new to you. However, electron configuration and periodic trends should not be new to you. So, what you'll need to do is as you go through this, obviously, you don't need to write down every little nitpicking thing, but you should write down, like, especially make your focus on how Coulomb's law relates to everything else. And then, of course, if there's things that you forget or so forth about electron configuration and periodic trends, you can catch up on that too. So let's go ahead and go to the main topic here, and that is Coulomb's law. And before we do that, we have to remember just the shell model of the atom. And so with the shell model, and I hate to say shell model, but we have to have some kind of graphical representation, although we do know that the quantum mechanical model is the way to go now. But we just have to think about where the electrons are in relationship to the nucleus of the atom. So remember, the overall charge of the nucleus of the atom is positive because you have protons and neutrons in the atom. Now, the electrons are obviously negative, and so there is an attraction between there, but the electrons are moving so quickly that they're not sucked directly into the nucleus. So there is a force of attraction, and it results simply from these opposite charges. Now, that force of attraction can be quantified, but we don't ever in AP have to use Coulomb's law to put numbers into it directly. Instead, we look at Coulomb's law more so as a relationship between the magnitude of charge and the distance of particles. That K constant that you see right there, I mean, we don't ever really need to calculate, so we don't need to worry about the K so much. We are more so worried about the Q's and the D's, and that equals our force of attraction. Now, the force of attraction, it does decrease as the distance between the outermost electron and the protons increases. So if you look at that, I mean, it just makes sense. So as the distance increases, and or the denominator of something increases, then your force is going to be smaller. As your charge increases and your distance is still small, then your force is going to be greater. So basically, we're looking at relationships here, not necessarily quantifiable things. So in the shell model of the atom, now let's relate it to Coulomb's law. So we know that these electrons move around the nucleus, okay, in the shell model, not the quantum model, okay? So we're just looking at this in terms of more so Bohr's model, which you know how much I love Bohr's model. But we have basically, just think about, we have a set quantized energy level. And that set quantized energy level basically goes back to energy level 1, energy level 2, energy level 3, and so forth, like when we do our electron configuration. But according to Coulomb's law, the forces of attraction between the electrons and the nucleus in N2 are less than the forces of attraction between the electrons and the nucleus in N1. And again, it's because Coulomb's law says that the greater the distance, go back to the distance here, when your denominator is bigger, then your force is going to be smaller. And if you think about that, and this is how a lot of times I explain this to you in Chem 1, but you can't use these, you have to use Coulomb's law on the AP exam. You can't say mama nucleus has less of a hold, but that's really what it is mama nucleus does have less of a hold on those electrons in the second energy level. However, because those electrons in the second energy level are further from the nucleus, therefore the force of attraction gets lesser. So again, we've got this is just for terminology here. Just make sure you use these terms, especially when we do our free response questions. Always valence electrons. We work with valence electrons all the time, but sometimes we don't give names to what's going on in the middle. And so we refer to those as inner core electrons. And those are what's between the valence electrons and the nucleus. Now, this should sound familiar to you, but this is the shielding effect. And so the shielding effect, think about successive shells are larger than the previous shells. So for example, a 1s shell is smaller than a 2s shell, and a 3s shell is bigger than 2s, and a 4s shell is bigger than 3s, and so forth. That's what we're talking about, successive shells. So electrons in successive shells spend more of their time further away from the nucleus. Well, that makes sense because the more energy levels you get, the further away you are from the nucleus. But those electrons in the outer shells are partly shielded from forces of attraction by inner core electrons. So let's think about this. There's a twofold here. First off, the outermost electrons don't have as much of a pull to the inner electrons because there's electrons in between the valence electrons and the nucleus. So there's less of a pull. But also you have to remember those core electrons have a negative charge, and those outermost electrons have a negative charge. So they still want to keep their distance because they're the same charge. So, and we know like charges repel. So again, the shielding effect, repulsion from the inner electrons, reduces these electrostatic attractions. Don't get wigged out by this word. Electrostatic attractions only means you've got negative electrons being attracted to positive protons or positive nucleus. So what is an orbital? And this is kind of gearing up toward electron configuration again. And if you recall the orbitals, they're s, p, d, and f. Now, an orbital it's a graphic representation. And it's a space that those electrons occupy 90% of the time. Now, it doesn't mean that it's always going to be there, but those electrons are moving so fast. We're just saying, hey, those electrons are spending most of their time there. It's just a concept, not a physical structure, but we put it in this conceptual form so we can help assign where those electrons might be most of the time. So for example, here we have a 1s sublevel. And so if you have electrons, and this is just showing a scattering of electrons. Now this representation is not showing how many electrons are there. Good gracious, there's tons of them if you counted. But it's showing more so like those electrons are moving so fast, so we can't necessarily follow one electron. So it's showing the spaces as to where the electrons have shown up. And so this is where the electrons can be found 100% of the time. But yet we are going to put like a sense of boundary around it. And it's not even an exact boundary. But if we said, hey, let's make this a certain picometer. Let's make this a certain distance from the nucleus. And that's going to be an area where the electrons are found 90% of the time. So this might represent our 1s orbital, or it could represent our 2s. But remember, an s orbital is spherical shaped. Now, if you recall, and I'm going to do just a little picture over here real quick, just for a p orbital. And so a p orbital looks a little bit different. And let me get a good color going on here. Okay, so a p orbital, and I know some of you guys kind of struggled with this in Chem 1, and especially what they might look like. So we have to think about here with a p orbital, we have to think about our axes. And so we've got our x-axis, we've got our y-axis. And a p orbital on the x is going to be like, it's kind of like an infinity sign, and that's a really poor drawing. But that just shows like one p lobe. And remember, 2 electrons can be in that specific space, but they're going to be in that space 90% of the time. And then, of course, with the p orbital, you're going to have one of those lobes potentially on the y-axis. So there's a second lobe that can hold 2 electrons. And so, again, those 2 electrons will stay in that space for about 90% of the time. But now you have the third dimension, which is a z. So we're going to pretend this is coming out at us. So pretend this is coming out at you, and you have a third lobe. And those third lobes can hold 2 electrons. And if you'd put all of those together on the axes, then you'd have one lobe on the X, one lobe on the Y, and one lobe on the Z coming out at you. Okay, so that means that those potential 6 electrons in the p orbital will be in that space about 90% of the time. Now, again, here's just another representation of our 1s orbital and the shape. You should know the shapes of s orbitals is a sphere. P orbitals, is kind of like infinity on every axis. Then you get into D and Fs, and there's just a lot of lobes. But one thing I want you to remember, and you know this from using the periodic table, is an s orbital has basically one lobe that holds 2 electrons. A p orbital has 3 lobes that hold 2 electrons each for a total of 6. A d orbital has 5 lobes with a total of 2 electrons in each lobe for 10 electrons. And finally, an f has 7 lobes for a total of 14 electrons. And you can figure that out using your periodic table too, because we know that if we count, that's the number of spaces going across each S block, P block, D block, and F block. Now, when we go to fill orbitals with electrons, just a little recall here. I just want to make sure that you realize that electrons are added to the lowest energy orbital available. And if you recall, that goes back to what's called off-ball principle. That's called the off-ball principle. So we fill electrons with the lowest energy levels first. It's just like building a house. You have to build the foundation before you can add anything on it. And this is because nature always favors lower energy systems, because it's actually like lower energy the closer you are to the nucleus. And so there's a format that can be followed to determine the lowest energy orbital available, and that goes to electron configuration. So if you recall here, the orbital filling order, we start at the top where hydrogen would be, and we have a 1s1, and that 1s1 comes from the first energy or the first energy level. The s orbital is these 2 columns here, and you have 1 electron. Now remember too, we have helium, and we kind of like put helium right next to hydrogen when we do electron configuration. Also, remember, as you go down the orbitals, you have 1, 2, 3, 4, 5, 6, 7. But when you get to the D, remember you go from 4s to 3d, and you go from 5s to 4d, and 6s to 5d, and 7s to 6d. And remember, that all has to do with the off-ball principle, because a 3d has a higher energy than a 4s, but a lower energy than a 4p. And then you come down here to the Fs, and even though 4F is actually in the row of 6S, we go 2 down. So instead of 6F, we say 4F, and instead of 7F, we say 5F. And if you guys need a recap of that, please ask me in class. Okay, just real quick too, when filling the orbitals, you have your principal quantum number, and that's your energy level. Quantum is another name for energy, and you're going to see that word quite a lot. The S is the orbital type, and again, the superscript is the number of electrons in that subshell. So another thing just to recall, and you guys should already know this, but isoelectronic species. So isoelectronic, and you need to get this word down pat. I know we've used it before in Chem 1, but this is something that comes up frequently, and the better you can use this word, the better off you'll be. But notice all of these have this exact same electron configuration, but some of them are ions. And it's simply because these elements have either gained or lost electrons and ended up being the same electron configuration as argon in this case. So as the ratio, if you see down there at the bottom, as the ratio of the protons to electrons increase, the forces of attraction on those electrons increase. And so we just have, when we lose electrons, then actually we have greater stability. So it's good for these ions, the ions are trying to seek this stability. Oops. Okay, and then we have, this is something that I've spoken about in my classes, but I'm not sure if you've heard about it in all the classes, and this is with the D blocks. And these elements lose electrons from their highest S sublevel first, before losing from their D sublevel. So let's think about this, and this is from the ionic version. Now, I will talk to you in class briefly about, excuse me, about, for example, D4 stealing an electron from the S. So D's have a higher energy than the S's. So S can only hold 2 electrons and D's can hold 10. So there's definitely more energy for the D's. And so the D's are able to steal from the S's. Now, most of the time, things don't steal from P's, things don't steal from D's, things don't steal from F's. We only steal from the S because the S is kind of like the little guy. So everything kind of bullies up on the S. But if you look where Fe2 plus, so you've got iron, and again, this is just the noble gas notation where you have argon, 4s2, 3d6. This is your typical iron. But what happens though is, let's say iron's going to lose 2 electrons. Well, instead of writing 4s2, 3d4, that's not very stable at all. And so what's going to happen is these 3Ds are like, I'm just going to take out those S's totally and give myself 6 electrons in the 3D orbital. And if you have an F3 plus, then instead of, so normally you'd have 4s2, 3d6, and you lose 3 electrons. Well, we're going to wipe out the 2 there, and then 1 has to be gone from the 3d5. So notice the D's are going to hang on to as many as possible when it loses multiple electrons. Now, this is what you've heard as effective nuclear charge, and I'm going to give you a quantifiable version of it. Now, we talk about effective nuclear charge, especially when we get ready to talk about these periodic trends that we're going to discuss. And officially, an effective nuclear charge is Z, and it's EFF. So Z sub F, meaning effective, and then Z is the charge experienced by an electron. So whenever you see Z, you're going to see a charge here. And so Z here in this case is the actual nuclear charge, and the sigma is considered the shielding constant. Again, you guys, thank goodness, but in AP chemistry and Gen Chem 1 and Gen Chem 2, you don't need to calculate such an effective nuclear charge. You just need to understand what it is. And at this point, we need to understand that shielding does have an effect on the effective nuclear charge. So really, the effective nuclear charge is how much an electron feels the charge. It's the charge experienced by this electron. And so when we have repulsive forces caused by the shielding effect, so caused by those inner electrons, and it reduces the effective nuclear charge experienced by the outer electrons. So when you have greater shielding, those outer electrons, or the valence electrons, are going to have a lesser effective nuclear charge. When you have electrons that are closer to the nucleus, those electrons have a greater effective nuclear charge. Now, let's go back to periodic trends, and I'm going to give you a quick recap of some periodic trends. And you guys, you need to make sure you know these, but also we have to be able to use these. And you're going to find that we use periodic trends to explain so many things within the rest of chemistry. So honestly, periodic trends is one of the most important things that you're going to need in chemistry. Okay, so atomic radius, again, it's the distance from the nucleus to the outermost electron. We can't just measure that because the electrons don't stop. So typically what we do is we measure the distance between the 2 nuclei of the same atom, and we divide by 2. That's the best way to do it. We can also do it theoretically. But more so for us, we are looking more so not at the quantitative part, but just using as comparisons. So we have going down a group from top to bottom. So when this is what we're talking about on the periodic table. So we have new shells that are being added. So we have one orbital, so 1s to 2s to 3s to 4s, and the energy levels are being added. So the valence electrons then have more energy. They're less stable and they're further from the nucleus because now we have lesser effective nuclear charge. As you go down the periodic table, we have greater shielding. There's a decreased effective nuclear charge because these electrons are further from the nucleus. So according to Coulomb's law, so you guys know about atomic radius, but now let's relate it to Coulomb's law. So the force of attraction decreases as the distance between the electrons and the protons increases. So let's think about this. If we're looking at, let's say, lithium versus, where am I at here? Okay, let's say we're looking at lithium versus francium. Okay, they're both alkali metals. They both have the same charge. So the charges are the same, but the distance from the nucleus to the outermost electrons is vastly different. So therefore, the force that is experienced is much lower for francium than the force experienced for lithium. So therefore, the atomic radius is going to be a lot bigger because the francium is experiencing way less of a force of attraction according to Coulomb's law. That's the kind of answers we got to work toward. So as we go from left to right across the periodic table, remember this one was kind of the weird one because we said, oh, we're adding more electrons in the same energy level in the same shell, but yet we're experiencing a grade of effective nuclear charge, okay? So the shielding effect will be similar, and these as we add more electrons to the nucleus, then we're going to have more of an effective nuclear charge that's going to pull the nucleus, it's going to pull those valence electrons in tighter. And it wants to hang on to those. The nucleus wants to hang on to those valence electrons. So let's say, for example, we've got, let's see, is it lithium versus neon? Okay, so we're kind of looking at the second energy level. Well, lithium has 1 valence electron, neon has 8 valence electrons. They both have electrons in the second energy level. So what we're doing here is the charge, the shielding effect doesn't increase a whole lot across it because there's not a whole nother energy level being added. So therefore, when you move left to right, there's more protons that are being added. So then we increase the charge. So what's happening with Coulomb's law, as you move left to right, the top is getting bigger. The charges are getting bigger, but the distance stays the same. So the charges are getting bigger, the distance stays the same. So if in any kind of problem, if the top gets bigger than the bottom, then your force increases. So again, that's where the effective nuclear charge increases. And if it's increasing, it's going to hold those electrons tighter. And actually, the atomic radius size will decrease. Now, ionic radius, cations. So this is going back to, we're comparing cations to anions. And remember, this is like when I taught you guys initially, this is what I like to do. So potassium, think about this. Potassium has 19 protons. And in this case, we've got 19 protons and 19 electrons in neutral potassium. But when we have potassium as a cation, we've got 19 protons and we're holding on to 18 electrons. So since we're holding on to less electrons with the same number of protons, our effective nuclear charge is actually greater. So because we have more protons here holding on to less electrons, they're able to be held tighter, so therefore the actual atom's going to be smaller. So that's why cations are smaller than their neutral atoms. Anions, on the other hand, are larger. So you've got chlorine, for example, and regular chlorine has 17 protons and 17 electrons. but chlorine minus has 17 protons and 18 electrons. So here you have less protons holding on to more electrons. So the actual effective nuclear charge is greater. So therefore, the size of an anion is larger than the neutral atom. Honestly, I think the best way to do this, instead of trying to memorize things, is compare the number of protons to the number of electrons and then use rationalization for it. Now, ionic radius going down a group from top to bottom. We've got new shells are added. They get larger orbitals. Valence electrons have more energy and are less stable. So again, we go to Coulomb's law, and that's the force of attraction decreases as the distance increases. So we're going back to Coulomb's law of distance increases, charge stays the same, therefore our force is going to be smaller. Same thing, just take a look at this here for a minute. You can put this on pause and look over it, but it's the same concept. So the increase in a positive charge increases the force of attraction and it decreases the size of the radius. Okay, so these are just reasons that, in terms of Coulomb's law, that can just help you with the wording. Same thing here. I just want you to take a minute and just kind of just read over this and just decipher this in terms of Coulomb's law. I didn't want to get rid of these slides, but I don't want to read them directly to you either. Okay, let's go to first ionization energy. Now, ionization energy is energy that's required to remove an outermost, least tightly held electron from an atom. Now, this says in the gas phase. Now, you guys, obviously, not all electrons are in the gas phase. But what we can do is when we study atoms, most of the time we study atoms by putting them in the gas phase because atoms are easiest to study when putting them in the gas phase. If you remember, even with the mass spectrometer, we had to ionize it first and we had to put it in the gas phase in order to do anything with those atoms. So you have to change the pressures and you have to change the temperatures in order to get those atoms in the gas phase because they don't like to typically go there. Now, the first ionization energy, notice here, hydrogen in comparison to helium. So helium has a much higher ionization energy. And remember from the periodic table, He has the highest IE, which helium has the highest ionization energy on the periodic table because helium, in fact, does have 2 electrons in the first orbital, which means it's held tightly. And so it's very difficult to pull that electron away. What I want to point out here with this is what we're looking at right here. And that lithium, so we're going from lithium to beryllium to boron. So this boron is like this weird little peak, and then there's a dip. And it more so has an effect to do with, if you think back to the orbital diagram. So let's say I'm looking at the 2p, and let's say I have 1 electron in the 2p. So that 1 electron in the 2p is going to be real easy to remove. Okay, so that 1 electron is going to be real easy to remove, but then when you have these, it's going to be more difficult to remove. And if you have like this, then it's going to be a little bit easier to remove that 2p4 than it will be to remove others. Then once you get to neon, it's going to take a very high ionization energy again because you have a very high effective nuclear charge. So again, here we have in comparison with hydrogen and helium, helium is almost twice the ionization energy of hydrogen. And it honestly has everything to do with Coulomb's law. And because helium has twice as many protons. So your quantitative, your Q's are going to go doubling and your D is going to stay the same. So therefore your force is going to double here. If the most loosely held electron in lithium was about the same distance from the nucleus as those in hydrogen and helium, we would expect lithium to be about 3 times greater. But what happens is lithium gets an electron in the next energy level, so therefore the distance gets greater. Okay, so we just want you to kind of see like why. And the hardest thing I think about ionization energy is it's the amount of energy required to remove an electron. So you need a high ionization energy because it takes a lot of energy to remove the electron. Electron affinity, I know you're not super familiar with this term. It goes very much hand in hand with electronegativity that we'll look at the end here. But electron affinity is the energy change that occurs when an electron is added to a gaseous atom to form a negative ion. So basically, we're like adding electrons, electron affinity. When you have an affinity for something, you like something. So these atoms want more electrons. So it's a measure of how much an element wants to accept another electron. And a lot of times, what I say the difference between electron affinity and electronegativity is I feel like that electron affinity is the quantitative version of electronegativity. Now we're going to find electronegativity is more like a ranking. So we have like a 0 electronegativity and we have a 1 and we have a 4, but it's not the amount, the actual calculated amount of energy, where electron affinity can be. Electron affinity has an exothermic and an endothermic value. So when the actual atom releases energy, it's exothermic. So when it wants to accept the electron, the more negative, the more it wants to accept the electron. So if we have a very much more negative exothermic, that's the worst it wants the electron. So we're talking like fluorine is going to have a very negative electron affinity, whereas the noble gases are going to have a very positive electronegativity or electron affinity because it does not want to accept the electron. Notice here also we have, the alkaline earth metals typically have a plus charge because they don't exactly want to accept another electron, because that's actually going to weaken them a little bit, because it'll throw one electron in the 3D or 4D, or it'll throw an extra electron in the 2p or 3p. Now notice this kind of like lone plus right here. And it's more so because it's so close to the nucleus, and it goes back to the orbital diagram. Okay, so we've got 2p and we're all good. And if we added another electron in there, it's just not going to work out so good. So it really doesn't want another electron, especially being that close to the nucleus. Again, electron affinity, you can read through this, so you can, again, just kind of like rationalize the group 2A and the group 8A as to why there's plus charges and why it's endothermic. And finally, electronegativity is an element's ability to attract electrons, or an element's desire for an electrons in a chemical bond. And we know that floozy fluorine, or we can say, like I think in the past I've said, fluorine has Riz. So fluorine really, really wants another electron, and fluorine literally will bond with just about anything. So those electrons, this right here, like make note of this. This is going to come out big time in the next 2 units. The electrons will spend more time around the more electronegative element in a chemical bond. So if fluorine is bonded with something else, those electrons spend the most time around fluorine because of that electronegativity, because of that attraction. And finally, just remember, noble gases, there's a 0 electronegativity. We're going to find that electronegativity is more so of a ranking from 0 to 4. And we're going to look at that more closely when we talk about bonding in Unit 2. Okay, and finally, electronegativity, we can always use Coulomb's law. Coulomb's law can be used to basically explain anything periodic trend-wise. So when 2 atoms are involved in a chemical bond, the bonding electrons will experience the greatest attraction. that is closest to them. So as the atomic radius decreases, electronegativity actually increases, except for noble gases because they don't want to bond. Okay, guys, so have your questions ready tomorrow and we will rock and roll. And you guys enjoy your day. Bye-bye.